Good morning, good afternoon. Welcome to ARA's Webinar Wednesday. I am Sri Rao, your moderator for today's webinar titled Development of Fast-Running Pavement Stress Prediction Model. Now I'd like to introduce our presenter, my colleague and very good friend, Dr. Ali Ashtiani. Dr. Ashtiani is a senior civil engineer and a licensed professional engineer holding a doctorate degree in civil engineering. He specializes in structural modeling of pavements, finite element analysis, and machine learning. He joined ARA in 2016, in May of 2016, and he has supported the FAA, the Federal Aviation Administration Airport Pavement Technology Research and Development Program while at ARA. His work includes a lot of things related to pavements, including pavement design, testing, and evaluation. And he leads the team that's responsible for developing, enhancing, and upgrading the Far Field FAA RFIELD program. So we're really excited to listen to what Dr. Ashtiani has to say in his presentation today. So I would like to hand it over to Ali, my good friend Ali, Dr. Ali Ashtiani. Ali?
Good morning, good afternoon, everyone. Thank you, Sri, for the warm introduction, and thank you all for joining today's webinar. Again, I'm Ali Ashtiani, and I'm excited to share insight on key advancements and challenges in airport pavement analysis and design. This webinar provides a quick overview of the FAA Airport Pavement Technology Program. Then it will explore airport pavement analysis and design methods with the focus on top-down cracking failure in airport rigid pavements. It will then discuss technical challenges in designing pavement for top-down cracking, and finally introduce machine learning model for rapid estimation of pavement stresses. So starting with the overview of the airport pavement R&D, since 1999, FAA has conducted state-of-the-art research on airport pavements at the William J. Hughes Technical Center in Atlantic City, New Jersey. National Airport Pavement Test Facility, NAPTF, is a full-scale pavement test facility within the FAA Tech Center that provides good quality, high quality, accelerated test data from pavements subjected to simulated aircraft traffic. Since 1999, 9 construction cycles have been built and tested that includes both rigid and flexible pavements. In September 2015, FAA expanded its full-scale accelerated testing capabilities with the addition of National Airport Pavement and Materials Research Center, NAPMARC, with a focus on pavement material performance. We at ARA have provided pavement consulting support to the FAA since 2015. The FAA Airport Pavement R&D program conducts research in areas of pavement design, pavement materials, and pavement evaluation, with the goals of designing safe, durable, economical, and environmental friendly pavements. The products of this research are sets of specification in FAA advisory circulars, specification for material characterization, and a series of software packages for pavement design, evaluation, or management. So as an example, Far Field is the FAA pavement design program where we have played a key role in its development, enhancement, and upgrades. So how the airport pavement design works? Pavement design is based on a mechanistic empirical concept as shown in diagram below. So it usually starts with defining a performance or failure criteria, which in our example, which is the airport rigid pavement, the failure criteria are typically bottom-up cracking and top-down cracking. So the procedure then uses a pavement mechanistic response model to calculate critical stresses associated with each of the failure criteria for a given pavement structure and an aircraft mix. The calculated stress will that gets sent to a failure model that relates the repetition of that calculated stress to failure. The failure criteria are defined based on pavement distress quantity. So this part is the empirical aspect of the design procedure, and FAA uses data from NAPTF full-scale test to establish the failure models. Next step is to calculate the damage index, which is defined as the actual repetition of the aircraft to the repetition of failure. Then the damage is calculated across the pavement and for all the aircraft using a cumulative damage factor or a CDF procedure. If this condition of the CDF is satisfied, the design is complete. If not, the procedure sends the output to a thickness optimization module to revise the thickness and send it back to the loop. So as you can see, the pavement design is an iterative procedure that requires numerous calculation of pavement stress and damage. And the stress calculation, this part, is the most computationally expensive part of the design process. This webinar focuses on the methods to mitigate the computational cost. The mechanistic models used in rigid pavement design program typically include models based on layered elastic theory. These models are fast, but not too accurate for rigid pavements. The other method is closed form solutions like the Westergaard's method. This is again fast, but it can accommodate very limited loading scenarios. The gold standard method for calculating the stress is finite element, which is the most accurate one, but it's computationally intensive. And direct use of them typically not practical for pavement design. The alternative method that is the machine learning models, which gained popularity in recent years. They're basically surrogate models that are trained based on finite elements. They're typically fast and has comparable accuracy with finite. The current FAA rigid pavement design only consider bottom-up cracking failure. So the stress calculation in far-field program is based on the three-dimensional finite element model. So far-field uses a quite simple model. It's used a single slab with a fixed size, doesn't consider any thermal curling. The aircraft load are applied at the edges of the slab, the fixed location, and the program calculates the maximum stress under the tires. So each run of the 3D finite element takes around 20 to 30 seconds. As discussed earlier, the pavement design uses the concept of cumulative damage factor, or CDF. A key aspect of CDF design is to account for aircraft lateral wander. So unlike highways where traffic is mostly channelized, aircraft rarely travel in a straight path along the pavement section in runways and taxiways. So instead, their movement includes lateral deviations known as aircraft wander. So FAA accounts for aircraft wander, basically say that the aircraft wander follows a normal distribution with a standard deviation of 30.4 inches. For example, if you have 10,000 passes of aircraft in your design mix, so the far field distribute the passes across the pavement width or the runway width using the graph shown here. The CDF procedure for bottom-up cracking first calculates the stress for each aircraft, then feeds the stresses to failure model to calculate number of passes to failure, or NF, then normally distributes aircraft passes across the pavement, and then calculate the CDF term for all aircraft and across all lateral offsets, and then combine all the CDF from all aircraft as shown in this example. So a typical design process takes around 10 to 20 minutes, depending on the number of aircraft in the mix and the pavement layers. FAA has a goal to add top-down cracking failure to the far field program and to the rigid pavement design process too. The top-down cracking is caused by high tensile stresses on top of the slab and is likely to govern the failure when an upward curled slab is loaded with a gear load near its edges. The top-down cracking typically manifests as a corner cracking or transverse longitudinal cracking. So how the top-down differ from bottom-up cracking? So these two contour maps, stress contour maps here, try to explain how they are different. So assume a pavement layer system. These are the jointed slab. assume that they're subjected to a negative temperature gradient, which means that they're curved upward, and they're loaded with an aircraft gear near one of the corner. So unlike the bottom-up, the maximum bottom stresses that occurs just below the tire footprint, the maximum top stresses occurs far outside the tire footprint, as shown in this dark red area. And the critical top stress can be critical in both directions. We're looking at the stress Y and X component can be critical. The next difference is that the magnitude and the location of the maximum top stress highly depends on the location of the applied gear with respect to the edges. So as you move the gear toward the center of the slab, the chance of top-down cracking will be minimal. And if you load it near the edges or corners, there's a high chance that you get the top-down cracking. And finally, the top stress can transfer from one loaded slab to an unloaded slab. So given all these characteristics of the top-down cracking, the mechanistic modeling requires the inclusion of thermal curling and using the multiple slab system as opposed to a single slab system used for the bottom-up cracking. This multiple slab system is used to accommodate full landing gear, which is critical in top-down cracking, to accommodate aircraft lateral movement, and to consider the load transfer between the adjacent slab. So a 3D finite element run for these complex slab configuration, pavement configuration, can take up to 30 minutes. So almost like 50 or 60 times higher than the typical run for the bottom-up cracking. So the design, the top-down cracking, the existing CDF for bottom-up cracking cannot be directly used for top-down cracking. So because the top-down cracking, the CDF for top-down cracking design requires calculating the critical stress for each point of the slab and for every transfer gear position and for each aircraft. And the stress must be calculated for in both directions, transverse and longitudinal direction. So this implies that the new procedure must provide more than just a single largest stress in the slab. It must provide the stress distribution across the slab for any lateral position of the aircraft. As you shown is the example. This is the pavement system that loaded with this gear and this corner. So we are looking to calculate the stress distribution along these pavement edges to be able to accurately calculate the CDF. So what's the challenge here? So to complete a CDF procedure for top-down cracking, we need to perform hundreds of finite element simulations. So you can see that the design can take few days, single design. So this indicates that the direct use of 3D finite element is not practical for top-down cracking design. So to address these limitations, FAA initiated research with the objective of first to develop a CDF procedure for top-down cracking, then develop a machine learning model that can support the design of top-down cracking. So basically the machine learning model will substitute the 3D finite elements for computation of critical stresses. And finally, the goal is to implement the top-down cracking in far-field program. So based on these requirements, we developed a machine learning model that takes some input parameters and estimate the stress distribution along the slab edges for a pass of aircraft. So our model consists of 19 parameters, total of 19 parameters, which includes the pavement properties, including layer modulus and thickness, joint spacing and joint stiffness, thermal loads, including temperature gradients and coefficient of thermal expansion, and the gear configuration, which includes the gear type, gear weight, tire pressure, dual spacing, tandem spacing, and track spacing. So for these models, we consider three pavement system. So first is the 4-layer pavement system that you typically use in large and medium hub airports that consist of a PCC slab on top of a stabilized base, sub-base, and subgrade. These pavement can accommodate, basically can serve heavy aircraft with gross weight greater than 100,000 pounds, and with the gear type with the dual tandem and dual tridem gears. The second pavement system is a 3-layer pavement system that are typically used as a rehabilitation alternative in the large hub commercial service airports, basically by eliminating the stabilized base and using a thicker slab, thicker PCC slab. And this pavement system can serve heavy aircraft like a 4-layer system. Finally, the third pavement system is the 3-layer system, which has a thinner pavement and used in general aviation airports. So this pavement can serve lighter aircraft with gross weight less than 120,000 pounds, and with the aircraft gear with a single aircraft with single and dual gears. So these research was done in 2 phases. So in the initial phase, we only had the 4-layer system, which is the typical pavement section in large hub airports. And then when we got done with the model was successful, and then FAA decided to expand those models. So then we included the 3-layer models. To train the machine learning model, we developed a comprehensive database by performing 3D finite element simulations using the FAA rigid pavement design program, FIFA. We use distinct combination of pavement and aircraft inputs to calculate the resulting stress distribution, sigma xs and sigma yy along these edges of the slab, of this design slab, which is the center slab in a 3x3 slab system. And we used 5-inch elements for all the cases to ensure the accuracy of the model. We used a Monte Carlo simulation that randomly choose the input values from a predefined ranges with uniform probability distribution for each simulation. So in total, we created 127,000 records of 4-layer system, 125,000 cases of 3-layer commercial service airports, and 125,000 cases for the 3-layer general aviation airports. So these tables show the inputs parameters and the ranges that consider for the database. So for 3-layer pavements, we had 9 pavement parameters, including the layer moduli, layer thickness, slab width and length, transverse the joint stiffness, and 2 thermal load parameters, the equivalent linear temperature gradient and coefficient thermal expansion. So for each input parameters, we defined a range of minimum maximum based on the FAA standard material properties and a far-field material library. So we use that as a benchmark, and then we extended those limits basically to include a wider range of pavement cases. For example, far-field uses a fixed number of PCC modulus of 4 million PSI for the design, but we included, we consider PCC modulus to be from 3.5 million to 6 million PSI to consider, high strength concrete. And for the temperature gradient, we used negative, the range was between -3 to 0. Pretty much, we assumed that the positive temperature gradient had no effect on top-down cracking. We used 4 parameters to encode a single aircraft gear. which includes the gear weight, tire pressure, dwell spacing, and tank spacing. And for each parameter, we define a min and max based on the far-field aircraft library. And again, we expanded those limits to basically accommodate any gear configuration or any gear configuration that comes in the future. So the gear parameters are independently selected in the Monte Carlo simulation, and so they do not necessarily represent a real aircraft. So this approach actually increased the robustness and generalization of the model, and it's basically eliminates the need for retraining the model every time and a new aircraft, a new gear configuration releases. So basically, our model is not aircraft specific. So instead, is a general model that can handle any gear configuration. So the single gear case were used to calculate the stress distribution along the x-axis and y in transparent longitudinal direction. So we also considered the full landing gear cases, like 2 belly gears of Airbus A380 or 2 belly gears of Boeing 747. Because the full landing gear, if applied at the same slab, can significantly increase the chance of top-down cracking. So we wanted to make sure that we account for that. So we have one additional parameters for the full landing gear, which is the track spacing, which is the spacing between the two gears. So these full landing gear were used to calculate the stresses in X direction only, because and then the single gear were used for the stress in Y direction, because these full landing gear has no effect really on the stress in Y direction. Its effect is mostly on the X direction, stress in X direction. Another parameter that we considered in our model was the aircraft lateral position or gear lateral position, which we show that has a significant effect on the magnitude of the stresses for top-down cracking. So the gear can vary from the third of the adjacent slab to the middle of the design slab. This is for the single gear, and so for the full landing gear, you can see that the gear can vary from here to there, and this location, were randomly selected in our Monte Carlo simulation. So another aspect that we consider was how the stress state on pavement changes as a result of aircraft rolling along the pavements. So do we need to simulate aircraft longitudinal movement like we did for the lateral movement? So the answer is no. So an analysis showed that the maximum top stress in the slab occurred when an aircraft actually enters the slab, as shown in these locations. So when the aircraft enters the slab, it caused the maximum top stress. So we don't need to really model the whole stress aircraft movement along the pavement. So the aircraft longitudinal position was not considered as an input variable in the machine learning model. So instead, their locations were fixed as shown here in these positions in the finite element simulations. So using the developed database, we trained a machine learning model that can estimate the stress distribution along this slide for any gear configuration for the predefined ranges of the input parameters. The model is a modular deep neural network, deep artificial neural network. So we, as I said, we had different payment systems. So we determined that the underlying physics from the 3-layer and 4-layer system are all the same. So we decided to combine the database from a 4-layer and 3-layer system to create a comprehensive database and developed a general pavement stress distribution model by leveraging from transfer learning. The machine learning model, the machine learning model has two major modules. One is the input encoding, and the other is the pavement stress distribution prediction module. The input encoding takes all the input parameters like pavement and gear parameters and process them into latent features, which are the compressed form of data. The latent feature will get sent to a pavement stress distribution prediction model to predict the stresses. So we first developed the general pavement stress distribution model, and from that we developed specific models for each 4-layer, 3-layer, and general aviation airports. This diagram shows the architecture of the input encoding module, which shows that it has a single architecture with a shared interface that can handle all gear type. We used multi-layer perceptron to process the continuous input variables like the pavement thickness and modulus, and we used embedding that translate the discrete variables like the gear type into the vectors that can be processed by the MLPs. So the output of this input encoding module is the latent features. The stress prediction modules take the input, the latent features, and estimate the stress in X and Y direction in two separate paths. So for the stress prediction, we initially use conventional deep learning regression models for discrete prediction, where the prediction are made over a domain with a fixed number of outputs. We use kernel function to basically approximate the shape of the stress distribution. However, since the output of the training cases were not on the same size, because we had different in a finite element case, we had different slab sizes in the database. So we had to interpolate the nodal stresses to a fixed number of points. So this was a constraint that significantly reduced the accuracy of our model. So instead, we developed a novel ANN model that instead predicts a dynamic functional for a continuous waveform prediction. So in this approach, there's no need for the model to specify a fixed range over the prediction domain. So the displacement in this figure is an abstract distance value across the waveform, the stress waveform, which has a dynamic size. For the model training, we used backpropagation and adaptive Hessian numerical optimization algorithm, which is a fast second-order stochastic optimization algorithm designed for machine learning. We used multi-task learning of the cost function, which is a function that the model tries to minimize during the training. So it has two objectives. One, to minimize the error near the peak stress area, which is critical for pavement design. The second was to minimize the mean square error of the entire stress distribution waveform, basically to encourage the model to learn a more generalized representation of the underlying physics. Here is an example of how the model works. So the model can predict the stress distribution in a fraction of a second. So for this example, which is a 3-layer system subjected to negative temperature gradient of 1.6 Fahrenheit per inch, loaded with two gear of Boeing 767. You can see that the stress distribution from the machine learning aligns very well with the stress distribution from ground truth finite elements analysis. The other example is again, a 3-layer pavement system loaded with two belly gears of Airbus A380-800. This is subjected to a negative 1.9 Fahrenheit per inch temperature gradient. You can see again a perfect match between the machine learning predicted and finite element calculated stress distribution. This table shows the overall performance of the model using a different performance matrix like root mean square error, R square, and others. So we can see that the general aviation model usually typically had the lowest errors, and the three-layer commercial service had the highest error. But the overall model for all the cases had the error of 3.9 psi. And the other observation is that the error for the prediction of the stress in X direction typically higher than Y direction because their database included the full gear aircraft, full landing gear cases, which are more challenging to estimate. You can see that R score all above 0.99. So another representation of the model performance shown in this table indicates that the 90% of the error across all the models were less than 5 psi, and 92% of the errors are greater than negative 3.95 psi for all the models, which means that the model underpredicts the stress, which is critical in pavement design. We want to avoid that. More than 3.95 psi in only 8% of the cases. These graphs shows the predicted and finite the stresses from machine learning prediction and finite elements calculation. You can see that very good correlation between them. And the one on the right side is a histogram of the error that shows the difference between the male predicted and finite element stresses. You can see that it rarely goes beyond 10 psi. So as a mean to validate our model, we wanted to see whether that 5 psi error is good or not. So we conducted some sensitivity analysis to determine the impact of the error from the model in the final thickness design. So we found that for some of the cases with the highest error in our database, the design thickness based on the machine learning model is within 0.5 inches of the design thickness based on the finite element model. So we consider this as an acceptable error because it aligns with the recommendation in the FAA advisor circular to round the design to the nearest 0.5 inches. Design thickness to 0.5 inches. And also in line with the common practice for contractors to increase the thickness up to 0.5 inches. So overall, the machine learning model will underpredict over the predicted thickness by 0.5 inches in less than 10% of the time. So for 90% of the time, the difference in finite thickness is less than 0.5 inches. So the machine learning models were developed using the PyTorch machine learning framework, and then we compile the models into a compatible DLL that's suitable for use in far-field program. So the deployment goal is to integrate the ML model into far-field as a drop-in replacement for 3D finite element simulation to be used in the airport rigid pavement design process. In summary, the machine learning model that we developed is practical for implementation of top-down cracking design. But the model is already implemented as a standalone library that can be used in far field. The model can return critical stress distribution in fraction of seconds. The model predicts entire stress distribution as opposed to just the maximum single stress, which is critical for top-down cracking design. The model is a generic model that supports any gear configuration, including full landing gear. And we invented a new machine learning model specific for this research. And finally, the thickness design with the ML will be within 5% of the thickness from finite element analysis. So this we published one report for the initial research, which included the 4-layer system, and we're publishing another report that includes the model from all pavement systems. It should be out very soon. So if you're interested to learn more about this research, you can read these reports. And finally, I want to thank the contribution of our ARA team, Aaron Williams, Dr. Tim Parsons, and Dr. Adam Amos-Binks. And specific thanks to the FAA, Dr. David Brill, the program manager who initiated this research and supported this research, provided very valuable good feedback. Mr. James Layton, branch manager at the FAA Tech Center, and Mr. Murphy Flynn, the airport payment section manager. Thank you all for listening. I'll be happy to take questions.
Ali, thank you very much. That was a really great work that you and your team have done, and I was very happy to see the great results that you produced under your research. For those of you who are in the webinar, you may now begin submitting your questions in the chat box. Send it to all panelists, and I will read them out or summarize them to Ali, and Ali will answer as many questions as possible in the remaining time. We hope you enjoyed today's presentation and that you will join ARA for future webinars. On the 29th of January, retired Colonel Marchant Collis will present Army sustainment challenges and new approaches to addressing them. Remember, this webinar was scheduled for November 20th, and if you've already registered, you do not need to re-register for the new date. So we had to reschedule that webinar, and it's going to be happening on January 29th, and you do not need to re-register. We do have many more webinars, topics that we are planning for 2025, so please watch your emails for updates, or you can always visit the Webinar Wednesday webpage, which is www.ara.com/webinars. So let's get to the Q&A portion of the webinar, and there are a few questions online that I would like to read to you, Ali, and I'm not surprised by this question. So the first question is, can the model be used in roadway pavements as well?
So the quick answer is no. So this is tailored for airport pavements because of the gear configuration that we use for the model, which is significantly different from the truck basically loads, truck tires. But I mean, the same concept. I mean, we can expand this model using the tire traffic, the truck traffic. But at this point, no, we can't use it directly for the highway applications.
But I guess just to kind of follow up on that, Ali, you could develop something similar with a similar concept for highway applications, correct?
Yeah, definitely. Yeah, we only need to basically consider the typical pavement section for highway, and the most importantly, the loading, the truck loading, which is different from the aircraft loading.
All right, thank you. The next question says, it's from Prajwal, who says, it's amazing to see the close accuracy of predicted stresses with the actual stresses. When the model was tested, did you significantly change the input parameters, or were the input parameters very close to the ones used for model training?
So thank you for the question. So yes, so for the testing, we set aside 20% of the data from our cases from the database for testing. So all the pavement model performance, the errors are coming from the 20% set aside, the test data set aside for testing. So it's an independent testing. But as I mentioned in the presentation, our model is not aircraft specific. So it's a it's a generic model that can handle any gear type. So we tested the model with some actual pavement cases, with actual pavement and with actual aircraft, basically. And we got the same performance for those examples.
So Ali, can you elaborate on that a little bit? So how did you choose the training database size, and how long did it take for you to run the finite element simulations and complete the database?
Sure, that's a good question. So the short answer again is we use trial and error. So our model included 19 input parameters that covered both the single and full landing gear configurations. So based on our prior experience, we estimated that 100,000 cases would be sufficient to model and learn the underlying physics of the problem. So after completing 100,000 cases based on some of the discussion that we had with the FAA and some feedbacks, we decided to expand the parameter ranges for some of the inputs. So we added more cases to the database to basically accommodate those adjustments. So we ended up with 127,000 cases for the original full-layer system. And so that was successful. And then for the follow-on research, for the 3-layer systems, we basically stick to that rule, and then we develop 125,000 cases.
So I think the next question, thank you, Ali. I think the next question is related to some of the discussions we just had on the last couple of questions. And you said 20% was set aside for validation. The question is from Wang Yuma is, has the proposed model, ANN model, been cross-validated or tested with new data? How was the R-square or root mean square error in the validation set or test set?
I mean, as I said, the root mean square and all the performance metrics that I showed is coming from the 20% of our database that independently used for testing. But those 20% were not used for the training of the machine learning model. And we also, I mean, we both, FAA and us, tested the model with some real cases from real airports, real aircraft, and we got the same performance. And even for our database, because the inputs that we consider for the database coming from a Monte Carlo simulation, which randomly picks value from each ranges. And some of the cases in our database are really not a realistic pavement scenarios, pavement design scenarios, like a very thin pavement with very heavy aircraft, something like that. So we use that option basically to increase the generalization of the model, and to basically to encourage model to learn the underlying physics. But in practical cases, those unrealistic scenarios return higher error. So in real world examples, you will get even less error from clear. So I mean, everyone welcome to test the model with some real cases. I'm sure you get this, the error that you get will be in the same range and even less.
Yeah, thank you, Ali. There's a lot of interest in your webinar presentation. So several more questions, and I'm going to go through them. I think you may have touched upon this, but what's the plan? Is the plan to update far-field version of the software so machine learning can be used during calculations? That's from
yes. That's the FAA plan to integrate these machine learning model and basically develop a new failure model based on top-down cracking. But what we did is just the analysis part. And FAA is currently working on revising or modifying the failure models specifically for top-down cracking, because the current failure model used in far field doesn't distinguish between the distresses caused by bottom-up or top-down cracking. Because, as I said, they use far field uses the failure model is based on the data collected in NPF, full-scale testing, and so FAA is working to segregate the stresses from top-down to bottom-up cracking to basically establish a failure model specifically for top-down cracking, which basically give the number of passes of a certain stress to failure. So that's the plan for far field. So in the next version of the far field, I can't tell when, but that's the plan. Maybe in coming years, in 1-2 years, you'll see that top-down cracking failure in far field.
Yeah, thank you, Ali. That's helpful to know. A related question, this work was obviously done for FAA, but can you use this for military aircraft, or did you look to see if this works for military aircraft, or did you consider military aircraft in your analysis?
Sure. I mean, we did not specifically use military aircraft, but most of them can still be used. I mean, can be analyzed with our model, except for some of the aircraft like the C-17 or C-5 that has more complex gear configuration that you need to tweak the model a bit to be able to use them. But the rest of the military aircraft with like a dual or single gear or dual tandem gear, they can all be, the model can accommodate those military aircraft. So the short answer, not all of them, but most of them.
All right, thank you. There's several quite technical questions, and the next one is from Makara Rit, and Makara says, I have some questions on how to model the LTE. Is it a spring model? And the multi-layer, are you using an equivalent thickness?
LTE means
load transfer efficiency.
Load transfer efficiency. I mean, I would refer you to the FIFA program that basically Farfield used to calculate the stresses. So the joints are modeled as a spring elements in FIFA with the defined stiffness for each spring, basically spring elements. So, but in the bottom-up cracking design, since the single slab is used, Farfield applies a 25% reduction to the calculated stress to account for the joints. But in FIFA, that can accommodate like a multiple slab system. The joints are modeled as a spring elements. So it's not based on the LTE, but the actual stiffness of the joint elements, basically the load transfer elements.
All right, thank you, Ali. Next question from Alberto Garcia. How do you avoid overfitting in its ability to continue to predict under a different database? I'm not sure I fully understand the question, so I'm just going to read it out. Hopefully, you can understand this question.
Yeah. So if I understand the question, so we used the Monte Carlo simulation basically to randomly choose values from different ranges, and based on that we construct our data cases for a database. So we want to make sure that we include the full spectrum of pavement and gear configuration. And so obviously when we train the model, we continuously tested the performance to make sure that it doesn't overfit, basically. So the 20% set aside data is basically used to to test the model, to test the performance, to make sure that there's no discrepancy between the error that we get from the training data and the testing data. And I said, as I said, this model is basically valid for the ranges that we considered for each parameter in this modeling. So anything outside these ranges should be used with caution. So I would expect higher error if you use like a, so for pavement thickness, we used from PC thickness from 8 to 24 inches. So if you use a 26 inches of PCC slab, you should expect higher error. So the model should be used within the limits of the parameter ranges that you use for the training.
Yeah, thank you, Ali. I think this is more of a comment than a question, but I'm going to read it out and you can respond appropriately. Dr. Kadim Kwar says, is this model for unreinforced concrete slabs? And I think it's a separate comment that we can increase the slab's length with the addition of reinforcement to reduce the number of joints. Can you care to address that?
I mean, our model is specifically developed for jointed slabs, not for the continuous slabs. So, so short answer is no, we can't use it for the continued reinforced in slabs.
How about composite pavements? The next question is from Murad, who says, is it possible to use this for a composite pavement, such as a rigid layer over an asphalt layer?
I mean, yes, we can use it because as long as it's we stick to the 4-layer or 3-layer system. So the wide range that we consider for the modulus of the layers should basically accommodate any base or stabilized base materials. So yes, you can use it. But you can use it for the composite, I mean the asphalt on top of the concrete pavement for sure, but you can use it for concrete on top of asphalt.
Okay, thank you, Ali. I believe you just responded to the next question, which basically says, is it also possible to predict the failure criteria for different pavement types? And I think you talked about that. The next question is, did you apply any non-dimensional input variable combining several individual input variables, or did you directly apply 19 different independent input types when you did your neural network development?
Sure. Good question. No, we used 19 independent parameters. We didn't use any dimensional analysis. I mean, the Pavement software for highway, or that the ANN model that integrated in that software, use a dimensional analysis, so combining some of the pavement parameters into one. So I mean, we didn't need to because our model is robust enough that can handle, 19 parameters. So we didn't have to. And basically, using this approach, you can test the model and then with, by changing any parameters when you in dimensional. So you don't have a lot of sense about if you like to increase the pavement thickness and slab thickness, you can see this impact on the model performance directly. But since our model, so the input parameters are independently defined in our model, you can basically evaluate the impact of each single parameter in the overall stress results.
All right, thank you, Ali. Here's a slightly different question. Voter wants to know if the model training data and setup included in a source code repository or GitHub or similar platform. If so, is the data, training data and setup publicly available?
Not yet. I mean, the far-field source code is in the public domain. You can download it from the FAA website, but this piece of it hasn't been posted in any in that domain. So I guess that when these is integrated into FARfield, the top-down cracking, the source code will be there. But again, I'm not sure because we provided the machine learning model as a dynamic link library, DLL, which so I'm not really sure if you would be able to see the source code of machine learning model. So because what we provide is an external link that FARfield can call basically. But I mean, we'll find out. It depends on how FAA wants to post it, the source code on its website.
Ali, I have to be honest, I have never seen so many questions in a webinar. This was really a hit. A lot of people have a lot of questions, and I cannot get to all of them today, but let's answer one last question, and then we'll wrap up the webinar. How is the impact of climatic factors incorporated in the finite element analysis or machine learning model?
I think the only environmental factor is the temperature gradient, the equivalent linear temperature gradient. That's the only one. So we use only the negative values because that's the thing. Because the positive temperature gradient has no effect on top-down cracking. Does that answer the question?
Yeah, I think that did. Ali, thank you. So we're running short of time, and I really appreciate everyone taking the time to put in the questions. I did not get to all of the questions, and we only have a few minutes. So if we did not get to your question, Ali has agreed to answer these questions for the next 24 hours via email, Ashtiani, AASHTIANI@ARA.com. It's on your screen. We just ask that if you please make sure your questions are not of consulting nature and understand that there may be some proprietary sensitivities around the topic that may limit his ability to respond, but Ali will take the time and make sure he responds to your question, and feel free to send him an email if you have any further questions regarding his presentation. I mentioned this at the beginning of the webinar. Again, on behalf of ARA, thank you very much for joining us today. Today's presentation is being recorded, and a link will be made available on the ARA Webinar Wednesday website sometime next week, probably early next week. We will also send a PDH certificate to all participants verified by our attendance report as present for the full hour of the webinar. A copy of today's presentation will also be included in that email we sent to you with your PDH certificate. Please allow us at least a few weeks, about 3 weeks or so, to receive your certificate. ARA is hiring. ARA is a great company to work for, very unique in that it's 100% employee owned. We continue to grow dynamically and are always looking for great people to join our team. So if you're interested in employment opportunities with ARA's transportation and infrastructure offices, please send a brief resume and your contact information to www.joinara@ara.com. Webinar Wednesday, joinara@ara.com. And thank you again for joining today. We hope you'll join us next week, next month, January 29th, for our next Webinar Wednesday, Army Sustainment Challenges and New Approaches to Addressing Them. Happy holidays, have a safe and healthy and happy new year. For those of you who are attending TRB annual meeting, Transportation Research Board annual meeting in January, please stop by ARA's booth, 731. Make a note of that. ARA's booth is number 731. And thank you very much again for joining. Have a good day. Bye.